If I were to ask you, what's the slope of this line, what would you tell me? Well, most people would say, well, we can kind of compare this to y equals mx plus b, right? Stuff we learned a bit earlier on where y equals mx plus b, and all we have to do is line up our equation right above y equals mx plus b. So you can see how the 3 is in front of the x here, so that lines up with the m, right? And we're adding 2, that means we're adding b, so our b is 2 in this case. And what that means is m is the slope, b is the y-intercept. The slope of this graph, of this line, is just going to be 3 because that's in front of the x. And the y-intercept is going to be 2, right? And it is, right here. Y-intercept is 2, and the slope is in fact 3. So when the slope is 3 on a graph like this, it just means if we move some unit distance, okay, so let's go from 0 to 1 in the x direction, that means we have to move up 3 units in the y direction. So if you can imagine this kind of extending up to 5, it kind of goes off of the grid. But if we move over 1 in the x direction and we move up 3, that's going to give us our slope, right? Because our slope is really just our change in y divided by our change in x. So this is our y2 minus y1, right? This is our y2 would be our 5, right? The y that we end up with, minus the y1, which is the y we started with. So all the way down here at 2, right? So that would be 3, right? 5 minus 2, divided by our x2 minus x1. So x2 is the x we end at, which is 1, minus the x we started at, which was 0. So this is just 3 over 1, which is 3. So the slope of this line is 3, and you're totally right. Okay, how about for something like this? Y equals 5x minus 8. Well, it's the same kind of thing, right? Where we start at -8 because that's our y-intercept, and every unit distance we move over, even if it was like 0.1 or whatever it was, we're going to move up 5 times that distance in the y direction. So our change in y divided by our change in x, that's going to be 5, because that's our m value, that's our slope. Okay, that's for linear functions. But what happens when we have something like y equals x cubed? Okay, how can you figure out the slope of this? Well, you can't really talk in terms of what's the slope of this because the slope here, right, of the line, the slope right there, it's going to be different from the slope over here, right? So they're different steepness, and like as you move further to the left, it's going to get steeper and steeper, right? As you move from the left to the right, it's going to get kind of shallow. It's going to shallow off over here. It's going to go to 0 right here, right? And as you start going to the right again, it's going to go steeper and steeper. So your slope or your rate of change of the function depends on what x is. You can't just say the slope is 3 or the slope is 10 because it's going to be different at different places. Like right here, the slope is 0, right? When x is 0, the slope is 0. But over here, like the slope right here, that's like looks like it's about 3, right? You could estimate it. So we could say like what's the slope at 1? Well, I don't know. If we kind of go this direction, 2 squares, we have to move like 5 to get there. So maybe that's like 5 and 2. Maybe the slope's like 5 over 2, which is 2.5 right there, maybe. But like, there's not really a good way to guess that, right? Because we would have to make this change in x infinitely small and this change in y infinitely small to even come close to what it actually is. Where in the examples we did up here, the rate of change wasn't changing, right? It was just 3 the entire way because this line was straight. It didn't matter what x was. No matter where you were, no matter how small your change in x was, even if it was just this little tiny square here, we're still going to move up 3 times that unit distance, which is why our slope is always 3, no matter how big or small. But down here, it's going to matter because it's not a straight line. So how can we find an expression to represent the rate of change of this graph no matter what x is? Well, I kind of touched on it before where the accuracy of our guess will depend on this change in x. Okay, so I'm just going to erase this and kind of start fresh. Okay, so let's say that we're trying to find the slope of this thing when x is 1. Okay, so we're going to find x equals 1, right? Draw a line straight up. And we're trying to figure out, it's called the tangent line. We're trying to figure out what the slope of this line here is, right? You can kind of see this triangle working, right? You can see this triangle going on where at x equals 1, that's the only point this line kind of skims the curve. Everywhere else it's not touching it, it only touches it at x equals 1. So what's the rate of change? How fast is this function increasing at x equals 1? Well, how can we guess that? Let's see. We can start at x equals 1, right, and kind of make a triangle where we go to the right, say 3 squares, right, and we can go up however many squares that is. I got to make this a bit bigger here. Let's maybe move over 2 squares just for the sake of room. So move over 2 squares. How many squares do we go up there? Well, we move over 2. We go up 1, 2, 3, 4, 5, 6, 7. Okay, so when our change of x is 2, our change in y is going to be 7. So 7 over 2, that's 3.5. Is that what the slope of this thing is at x equals 1? Well, no, because the slope, like this number here, it's going to change depending on what this is. Because let's say we didn't move over 2 units. Let's say we just move 1. So if we move over 1 unit, and we go straight up to hit the line, well, we're going up 1 here, and to meet the line, we have to go up 3. So our slope here, it's going to be 3 over 1, which is 3. So it just went from 3.5 to 3, just like that, right? So it depends on what your change in x is. And now let's actually think, how can we get an exact answer for the slope at any given value x? Well, we're trying to make this change in x infinitely small. So we're going to use what we know about limits. Okay, so the terminology that we use for the slope of a tangent line, that's what this is, a tangent line, of any given x value on a function is called the derivative. Okay, so the way this question might be worded is find the derivative of the function y equals x cubed when x equals 1. So that's essentially what we're trying to do. We're trying to figure out how fast is this function increasing, or what's the slope of this tangent line at x equals 1. Okay, so what we're really doing is we're finding the change in y over change in x, right? And up here I even wrote it, right? Change in y over change in x. When the change of x is essentially like infinitely small, it's basically 0. Okay, so the way we write that is instead of change in y over change in x, we write it dy over dx. Okay, like delta y over delta x. That's kind of how I remember it. Because people say delta y over delta x, that triangle just means delta. Well, you can think of this d as kind of a delta, except the change of x is basically 0. Except you might remember, if change in y over change of x is your slope, we can't put 0 on the bottom. So if we always just put 0 on the bottom, we get an infinite answer, and that's not what we want. We're not going to get anything accomplished by putting 0 on the denominator. Okay, so what we do is we say, also another notation for dy over dx, it's also called f prime of x. Okay, so this little apostrophe just means the derivative of the function f of x, so f prime of x. You also might see it, this isn't very common, but it's Newton's way of notating it, like x with a dot on top. There's kind of a bunch of different ways you can write it, but that's not super important. Like sometimes you might just see f prime. You might see like df over dx, or d by dx times f of x. It's all the same thing. It just means what's the derivative of f of x? That's all this stuff means. So for right now, let's just stick with dy divided by dx. Okay, so what's our change in y divided by our change in x when x is infinitely small? Okay, so let's use what we know about limits. Okay, so let me just write it down here. So I'll write dy by dx. That's going to equal the change in y divided by the change in x when x is infinitely small. Okay, so let's just call that change in x h. That's typically what people notate it with. So the h will just be however far we move to the right. Okay, so that's our change in x. So we're going to say that the derivative of y with respect to x is going to be the limit of the function as h gets closer to 0. So this basically means as the change in x gets closer and closer and closer to 0, close enough that we can basically say it is 0. So the limit of the function as h approaches 0, and the function is just going to be x plus h squared, right? Because this is, or not x squared, sorry. This is going to be x cubed, right? Because our function was y equals x cubed. Okay, so instead of putting x here, we're going to put in x plus h, because this is our change in x, right? And we're going to subtract the original y we started with. So this is our new y after we add h in the x direction. We're going to be subtracting x cubed. So this is our y2 minus y1. y2 is x plus h cubed, right? And y1 is just x cubed. So y1 is always your original function, and then your new function, your y2, that's just inputting the plus h after the x, wherever you see the x. Okay, so we're going to be dividing that by h. Okay, so this really is just change in y over change in x, right? Because our change in x is h, and our change in y is just y2 minus y1. Okay, so how can we simplify this? Well, let's actually do a question to kind of simplify it, because this is the definition of the derivative for our equation y equals x cubed. But if we wanted to write it generally, okay, how you write it is the derivative of any function, so dy by dx, is going to be the limit, okay, as h approaches 0, of f of x plus h minus f of x. Okay, so like I just said before, we did it with x cubed, but all we're doing is we're putting x plus h into the equation where we see x. So everywhere we see x in our equation, we're going to put an x plus h minus f of x. So that's just minus the original equation divided by our change in x, which is just h. So it's close enough to 0 that we can pretty much call it 0. It's infinitely small, except if we put 0 on the bottom, it's going to give us an infinitely large answer, which isn't going to be a real number. Okay, so this is called the definition of the derivative. Okay, so this is just your change in y divided by your change in x. That's all it is. It's basically grade 10, right? When you learned about slopes, change in y over change in x, except now we're incorporating what we know about limits, so we can apply it to functions that aren't straight, right? To functions that aren't straight and have curves in them. And we can now analyze them more effectively at different x values. Okay, so your derivative with lines that are curved like this, they're going to have like the expression you use to write the derivative will be x dependent, right? It'll depend on what x is, what your derivative is. Okay, so let's actually do a question here. Okay, so let's use what I wrote up here, x plus h cubed minus x cubed. Let's expand that and see what we can get out of it. Okay, so the derivative of x cubed is going to be the limit as h approaches 0, like I said, x plus h cubed. Okay, if we expand that, right, that's just x plus h times x plus h times x plus h. And instead of writing it like over and over and over again, I'll just kind of simplify it for you, all right? So if we have x times x, right, obviously we're just going to get x cubed from that. Okay, so we're going to get x cubed there. Actually, I'll write it just to kind of explain how we get the expansion. So x plus h, got minus x cubed there. Okay, so we did the x times the x. Let's do it one step at a time. So we're just focusing on the first two brackets here. X times x, that's going to be x squared. And then we're going to get plus 2xh, right, plus h squared. We get x plus h minus x cubed. So I'm just simplifying our change in y on the top. This is the numerator of our derivative. Okay, so we got this bigger bracket now. Let's do x squared times x, so that's x cubed, right? Let's do x squared times h, so plus hx squared. 2xh times x, so that's going to be plus 2x squared h. Okay, and then we're going to get 2xh times h, so that's going to be plus, so we got 2xhx squared, so plus 2xh squared. And we're going to get h squared times x, so plus h squared x. And we're going to get plus h squared. I didn't fit this in properly, but we're going to roll with it. So plus xh squared plus h cubed. So if we simplify like terms here, right, we only have one x cubed, right? And remember, we're subtracting this x cubed. So I'm going to attach this minus x cubed there. And actually, I included a number I didn't need to here. Hold on. So we did all the expanding. We got x cubed. We got the h cubed. We got the x or h squared times x, and then I just forgot. So it's gonna be x cubed minus, or sorry, h cubed minus x cubed. So you'll see all these x cubes are gonna cancel. Now we're gonna have h squared plus 2x squared h. So what combines here? Well, this is h times x squared. This is 2h times x squared. So we're gonna have 3h times x squared. Okay, and then we're gonna have 2x times h squared, and then plus 1x times h squared. So that's going to be plus 3x squared h. Okay, and then we're going to have plus h to the 3. Okay, so this is the simplified version of our numerator. So that's going to be 3hx squared plus 3h squared x plus h cubed. Okay, so I'm going to erase all this and kind of translate it to the top here. So all we did was we just expanded the top and simplified it. Whenever we have cubics, it can take a bit of time, but that's all we're really doing. So instead of writing x plus h cubed minus x cubed, all we're going to do is we're going to write it as it was 3hx squared plus 3h squared x, and then we get that plus h cubed. Okay, and then we had it divided by h. Okay, so how can we simplify this? Well, notice how every single term on the top has an h in it, and we're dividing by h. So if there's an h on the top and the bottom, we can reduce the power of the h's on the top by 1 and just cross out this h on the bottom. Okay, so essentially we could factor an h out of everything on the top, divide the top and bottom by h, and we would be left with 3x squared plus 3hx plus h squared, because we're just reducing the power on the h's by 1. So there was only one h with the 3hx squared. That's gone, so we just get 3x squared. 3h squared x, we're reducing that by 1, so we just get 3hx. It was h cubed before, just reducing that to h squared. Okay, good. So now that we have this, we don't have any fractions. So there's nothing wrong with plugging in h equals 0, because that's basically what it is. If it's infinitely small, it's close enough to call it 0. So we're confident in saying that the limit as h approaches 0 of 3x squared plus 3hx plus h squared is just the function evaluated when h is 0. So it's going to be 3x squared plus 3 times 0 times x plus 0 squared. So see how every term with the h in it is gone now, because 0 times anything is just 0, and we're left with 3x squared. Okay, so this is the equation we can use for the derivative of x cubed. Okay, the slope, or the slope of the tangent line for any given x value on y equals x cubed, the slope is going to be, we can write it y prime, is 3x squared. Okay, and don't worry, there's an easier way to do this with polynomials. I'll show you in a sec, but let's just do one more example here. So let's say we wanted to find the derivative of y equals x to the fourth now. Okay, instead of x to the third, it's x to the fourth. Well, we know that the limit as h approaches 0 of f of x plus h minus f of x over h, that's going to give us our dy by dx, right? So everywhere we see x plus h, or everywhere we see x, we're going to write x plus h for our f of x plus h. So it's going to be the limit as h approaches 0 of x plus h to the fourth, right, minus x to the fourth. Okay, so the one you're subtracting is always the original function, and then x plus h is always going to be your input for x of the original function, divided by h. And like we did in the last question, we can just expand this and simplify. So I'm just going to save us a bit of time here. Once you simplify and subtract this x to the fourth, your numerator, right, we still have this limit. Your numerator is going to be 4x cubed h. Okay, and you could do this on your own if you wanted to, just to verify that it's right, plus 6x squared h squared. Okay, plus 4xh cubed plus h to the 4. Okay, all divided by h. So these x to the fourth terms are gone because they were subtracting. So now it's simplified, expanded, we're all good. Now, like in the last question, we're just going to divide everything by h. So this h is gone. This h squared is just h. This h squared is just a 2 now. This h to the fourth is a 3. And this h is gone. So it's the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And like in the last question, we can just input 0 wherever we see h. So this is going to equal 4x cubed plus 6x squared times 0 plus 4x times 0 squared plus 0 cubed. Okay, so everything with a 0 in it, it's gone because 0 times anything is just 0. So this is like 4x cubed plus 0 plus 0 plus 0. So it's just 4x cubed. And you might notice a pattern. Okay, because in the last one, we started with x cubed and we got 3x squared. So it seems like this 3 came to the front and the exponent reduced by 1. And if we take a look at this one, we started with x to the fourth, and it looks like we brought this 4 out front and reduced the exponent by 1. And that's exactly what we did. Okay, so this is called the power rule for polynomials, and you can only use it with polynomials. You can't do it with like e to the x plus the natural log of x. Like there's not really a power rule we can use for that. We'll learn ways to find the derivatives of those functions, but we can't use a power rule only for polynomials, okay? So using the definition of the derivative, we can find what the slope of this thing is going to be. So let's say, what's the slope of this going to be at x equals 0? Well, we kind of predicted it before, right? It looked like it was flat. Okay, so we would predict that the derivative of the function at x equals 0 is 0. Well, we know how to use the power rule now, and we know the derivative of y equals x cubed, right? We know that y prime, or dy over dx, is 3x squared. We can figure out what the derivative is at 0. So we just plug in 0 for x. Okay, so y prime at x equals 0, that's going to be 3 times 0 squared, which is 0. And that's why the derivative of x cubed at x equals 0 is 0. Okay, what about this point right here that we were originally looking at? Well, we know that, I'll write dy by dx this time, just for some different notation, is 3x squared. Well, at x equals 1, it's just going to be 3 times 1 squared, which is 3. And remember, originally we had like 3.5 and all these different guesses, but now we know if we zoom in infinitely close, the slope of this tangent line is going to be exactly 3. Without guessing, that's with exact precision. Okay, using the definition of the derivative and also the power rule. Okay, so that's what derivatives are, and we can kind of relate this to what we were doing before, right? We could also use the power rule for y equals 3x plus 2. Okay, so for y equals 3x plus 2, how could we find the derivative of this? Okay, so we're going to go the dy by dx. Okay, well, using the power rule, the imaginary exponent on the x is just 1. So if we bring the x out to the front, or the 1 out to the front and multiply it by the 3, we're going to get 3 times 1, which is just 3. And we're going to reduce this exponent of 1 to 0. So this is like 3 times x to the 0. Well, x to the 0 is just 1, so this is just 3. And obviously 2 is a constant, so anytime you're taking the derivative of a constant, it's going to be 0, right? Because if you were to graph y equals 2, you would just be on this line forever. And it's not changing, its slope is 0, so its derivative is 0, its rate of change is 0. So it's going to be 3, which is the derivative of 3x, plus 0, which is the derivative of 2, which is 3. And that's why m is 3. Your slope is 3. Okay, so you can apply it to stuff you were doing in grade 9, grade 10, grade 11, right? Or just stuff that you learned earlier on. And you can also apply that same method to functions that look a lot more difficult. And you can do the same thing. Let's try y equals x to the 7th plus 3x to the 3rd plus 8x. Well, if we're finding y prime, we bring the 7 out front. So it's going to be 7x, reduce the 7 by 1, so that's to the 6th, plus, bring this 3 out front, multiply it by the coefficient that's already there. So 9, reduce this exponent of 3 by 1, so 9x squared. Okay, imaginary 1 here on the x, bring it out front, multiply by the 8. So 1 times 8 is 8, right? Reduce this exponent of 1 by 1, so it's x to the 0. 8 times x to the 0 is 8 times 1, so it's just going to be plus 8. So this is the derivative of that function. And you can imagine if we use the definition of the derivative, we'd be expanding this all day, right? Because this power, this x to the 7, that's pretty big. So if we did x plus h to the 7th, that would be x plus h times x plus h times x plus h 7 times. And then we'd have to simplify that and do all this stuff. We'd get the right answer, but the power rule is just a quick and easy way to figure out what the derivative is. So I hope this helped, this introduction into what derivatives are, the definition of the derivative, and how we can use the power rule kind of as a derivation of the definition of the derivative. So we're going to dive more into derivatives super quickly, and they're kind of a really neat tool in calculus that we can use. But I hope that this kind of taught you that in grade 9 and 10 and earlier on in your math career, you use derivatives. You just didn't know it, right? So now that we know what derivatives are, we're going to be able to rapidly expand upon them, right? And do some pretty cool things. So I hope you kind of followed along in this video, kind of understood where I was going. And if not, just go back and rewatch it because we covered lots of heavy stuff. I totally understand. But yeah, so derivatives are super cool. We're going to be able to expand on them next video. So just stay tuned and I'll see you in my next one.